In this video, I'm going to try to further draw a connection between Buddhism, and in particular the teachings of the Prajna Sutras, or the Wisdom Sutras within Great Vehicle or Mahayana Buddhism, to the notions within quantum physics, which I think are consistent with the teachings of Prajna. And in particular, I want to focus on a video that helped me understand more fully the notion of entanglement within quantum mechanics or quantum physics. And again, I make no claims whatsoever at having any kind of a deep knowledge of this subject. But I do think it's worth looking at, and I think it's worth pointing y'all to as you travel on your own spiritual journey and or your own journey toward trying to establish an understanding of the nature of reality from a scientific perspective. So, here goes, and I hope this is something that somehow makes sense and has meaning for you in your own journey.
So we have a conference here about entanglement, and so I thought, why not give a talk just about what entanglement is? So you all learned in elementary school, probably before, that if you want to add stuff up, it doesn't matter how you do it. So if you want to add up the chairs in this room, you can organize them by columns, count the columns, right? Count the number of chairs in each column, and then add the whole mess together. That's why we have multiplication. Or you can do it by rows. Or I can add up those chairs, and these chairs, and those chairs. It doesn't matter how I do it. So I think this is the most important equation in physics. And for all of you who are physicists, you can think of these terms as terms in a Hamiltonian. So I'm going to try to convince you that quantum theory follows from the additivity of the Hamiltonian. But if you're not a physicist, don't worry about that. Just think of these as any arbitrary things at all that you're adding up. So what you learned back in elementary school was it doesn't matter where you put the parentheses when you're doing addition. Okay, so do a little experiment. I want everyone to look around the room. Okay. Now I bet all of you are seeing lots and lots of parentheses. So for example, most of you are putting this thing and this thing and this thing in parentheses. And you're saying, that's one entity right here, right? Parentheses. And no one, I bet, no one in here is putting this thing and that camera over there in parentheses and saying, that's one thing. Okay? This says it doesn't matter. Those parentheses make no difference at all. So I want you to look around the room and make all the parentheses disappear. Not very easy, is it? Okay? It's hard to make the parentheses disappear. But that's what physics is about. Physics is about erasing all the parentheses and then putting in parentheses only where we want them and nowhere else, okay? And then being very willing to erase those parentheses. And the reason classical physics doesn't work, I believe, and I'll try to convince you, is that it slides into our natural belief that some of the parentheses have to be there, and that some of the things that we call objects are actually objectively there. You got to pay attention to the equation. Parentheses don't matter at all. So when you're looking around the room and saying, okay, I'm going to make the parentheses disappear, you're doing the next slide. You're saying, I'm the observer, and there's the world. And we're interacting. And there are no parentheses in the world. So that's how we want to think for a little while. And that's going to tell us about entanglement. So there's a very important case that we need to think about if we're going to try to think this way. And that very important case is that when I'm looking at my world out here, I see lots of observers. And when you're looking at your world, just outside your eyeballs, you're seeing lots of observers. Next slide. So when you're looking at your world, you see me. And when I'm looking at my world, I see you. But the parentheses don't make any difference to our worlds. So whether you treat me as a thing in your world doesn't make any difference to the world you see. Because the world you see is just your world. And I happen to be in it. But you can draw the parentheses or not, and it doesn't make any difference to your vision of your world. That's the fundamental thread that we're going to pursue through this talk, is you can erase the parentheses and it doesn't make any difference. So next slide, please. So actually the world is full of observers. All of us, we're observers. But because we can erase all the parentheses around us, we're not things at all. And in fact, nothing in the world that we can erase the parentheses around is a thing. So we're just the same as any other kind of thing that you can erase the parentheses around. In other words, next, there's nothing special about observers, at least in physics. Nothing special at all. Observers are just physical systems, which are just parentheses that someone's drawn. Okay? Now, you can flip that around and say it the other way. And if you flip it around and say it the other way, it comes out, everything there is an observer. So people ask me, does that mean computers are observers? What about electrons? And I say, yes, they're all observers. There's nothing special about observers at all. Nothing, nada. Okay, this is why physics is possible. Because if there was something special about observers, or for that matter, if there was something special about this podium, then you wouldn't be able to erase the parentheses around this podium, and you wouldn't be able to add things up regardless of where the parentheses are. And that bit of addition, if math didn't work that way, physics would be impossible. We wouldn't be able to do it. So parentheses being unimportant is why we can do physics at all. And what that tells us is there's nothing special about observers. So next. Okay. So we can now rewrite our equation just with graphics and say, here's the world full of observers, and I can cut the world up any way I please. So I'll cut it up in two, and I'll put some of the observers over there and some over here. But remember, that makes no difference at all to the world. It's just a parentheses. Okay, next, please. So these things are part of one universe, right? Universe means one. All this multiverse stuff is crazy. Forget about that stuff, okay? Universe means one. We're all part of the same universe. And so any parts that we cut it up into are interacting, and our cutting it up into things is just drawing parentheses, and they don't matter at all to anything. Okay, next. So this picture, where I cut the world up, is exactly the same as this picture. Why? Because everything's an observer. So this, even though it's got lots of little observers inside, the whole thing is a big observer. So I can rewrite this picture as that picture, and they're absolutely the same. It doesn't make any difference to the physics whatsoever to draw it this way or this way. And it doesn't make any difference at all to this interaction that I've represented by the double arrows. That's just an interaction going on in the universe that I've created by drawing parentheses and saying, okay, now I've got two things. So all the stuff that the universe is doing, I now have to represent as an interaction between two things. Okay, so next. Okay, so now we have another equation, but it's in words. Because we can do what we did in the last picture, we can take a cutting up of the universe and replace part of it by an observer. We can infer that observation and physical interaction are exactly the same thing. There's no difference at all between observation and physical interaction. But observation we think of as the transfer of information. And in particular, we think of it as the transfer of classical information. That just means information that one can write down on a finite page. So, or record in binary numbers or something like that are finite. So if observation and interaction are exactly the same thing, then classical information transfer is exactly the same thing as physical interaction. But if you talk about either interaction or information transfer, what you've done is draw an imaginary boundary, i.e. you've inserted some parentheses in the world somewhere, and you're thinking of the information as being transferred across that imaginary boundary. So we're going to represent that like that. Okay. So observation equals interaction, and both of those are just information exchange across an imaginary boundary. And at the panel this morning, there was a bunch of discussion about, is observation and action the same thing? And the answer is interaction. Goes both ways. So if I do something to the world to make an observation, I'm acting on it. And that's what Heisenberg figured out in the 20s, and it led to the whole Heisenberg microscope idea, where if you were looking at an electron, you had to bounce a photon off of it, and the photon perturbed the electron, and that's why we had the uncertainty principle, because you couldn't actually make an observation without perturbing the system you're measuring. Now, of course, that's right? All observation is interaction. What Heisenberg didn't do was flip it around and say all observation is also interaction. Observation is just physical interaction, nothing else. There's nothing special about observation. So there's nothing special about observers. Okay, one more. So, quantum theory. What is quantum theory? Quantum theory is the minimal, simplest theory that's consistent with an absolute identity between physical interaction and information exchange. And I will happily show anyone who's interested in it how to derive the Schrodinger equation from that. But I do want to give you one little piece of detail because I've got enough time. So, would you go back a few slides and I'll tell you when to stop? There. Thanks. Okay. So, if interaction and observation are exactly the same thing, let's think very carefully about this diagram and what it says. So, you are looking at your world that I happen to be in. But the parentheses you've drawn around me don't make any difference. You could erase those parentheses. What that means is that my interaction with the world, which is defined physically at my boundary, doesn't make any difference to what your interaction is, which is defined at your boundary. Because your interaction, which is this, is defined right at you. It's perfectly local to you. It's defined at the interface between you and your world. And my interface with my world is in here. And that doesn't matter to you because you can erase those parentheses and that boundary goes away. And when the boundary goes away, the interaction is not defined because the interaction's only defined at the boundary. Okay, now what does that tell you? That tells you that whatever I'm doing up here is affecting your world. But your interaction with the world doesn't change because your interaction with your world is defined at your boundary. And what I'm doing up here is defined at my boundary. So my interaction doesn't matter for your interaction. Okay? It matters for your world, but it doesn't matter for your interaction with your world, which is defined only at your boundary. So, right, Einstein here was wrong in thinking that entanglement had something to do with non-locality, because the observer's interaction is perfectly local to their boundary with their world, and none of the other parentheses make any difference at all. Okay, so what I've just done is demonstrate to you that what's called the no signaling theorem is true in a very strong form. The no signaling theorem says that two observers who are space-like separated cannot use a shared quantum system as a classical communication channel. Now, what I've told you is that we, you and I, cannot use the world that's between us, this blue stuff, as a classical communication channel. Because my interaction is by definition not correlated with your interaction. Your interaction is defined specifically at your boundary, and your interaction is independent completely of whether my interaction with the world is even defined. You can erase me, you can erase the boundary, can't erase the stuff, you can erase the boundary. The interaction is then gone, and your interaction does not change at all. Now, what that means is that I'm not communicating information to you. Your world is communicating information to you because you're interacting only with your world. And the information is flowing from your world to you. And of course, I'm communicating information to my world, but the world is in between us. And there's no classical communication channel between me and you because the world's in the way. And neither of us exerts any control in that world at all. You do not know that I'm standing here. All you know is that you are experiencing a world that is talking to you and doing a bunch of other stuff, like keeping you warm and keeping you in one place and all that. So that's something that skeptical philosophers have been telling us for thousands of years, and of course the Eastern traditions have been telling us for thousands of years. But science starts to take it seriously with quantum theory. So, because we have the no signaling theorem, we know that a very large fraction of quantum theory follows just from this simple equation I showed you. Because the no signaling theorem is a lot of quantum theory, and it's almost all of special relativity. So as long as you have that simple equation I showed you that says how you add things up doesn't matter, parentheses are not important, you get special relativity for free. Okay? Because you have the no signaling theorem. Okay, let's go forward. So let's go back to this imaginary interface, which is the imaginary boundary that is drawn around you that I could erase, even though you can't, and ask, what is this boundary? Well, it's exactly an interface in Don Hoffman's sense. Don's back in the room. And he'll be telling you about this stuff tomorrow, and he told you about it last year at this meeting, and he's been working on this for years and years and years. But what it is a boundary at which classical information appears because it's a boundary at which classical information is defined. And if I grab this boundary and yank it out of the picture, then this big I ends up back inside this cloud, and there's no distinction between them. They just become parentheses. I have to stick the imaginary boundary in to get any classical information at all in this picture. So classical information is just bits that are painted on because they're defined at an imaginary boundary. Now that idea is called holography in high energy physics and cosmology. And it was originally invented to deal with information storage by black holes. But it actually applies exactly in this case. Interaction, physical interaction, passes through an imaginary boundary and bits get stored on the boundary. Okay? Now, those bits are what we call the experience of individual objects. Those bits are, for us, parentheses. But for the physics, they're not anything at all. They're just an abstraction, just a little model that our temporal lobes build for us very kindly. So, classical information appears at that boundary, and it's what defines the interaction between the observer and the observed. But physically, there's no boundary, and physically, there's no interaction. So, again, as was said by someone in the panel today, physically, nothing ever happens. It's like the Talking Heads' old song about heaven. Right? There's nothing going on until you draw an imaginary boundary, and then lots of stuff is going on because interaction's passing through that boundary. Okay, let's see if I can get this right. So, what is entanglement? Entanglement's just the condition of interacting with the world through an imaginary boundary. It's the boundary that's an imaginary thing. And the interaction's just proceeding through that imaginary boundary. And that's why we've got classical information, i.e. measurement. So the measurement problem is nothing. The measurement problem is an artifact of us drawing a boundary in the world and saying, oh, there's classical information there, it must be objectively real. But it's not.